Now passing the left and the right subtrees of the root. This function handles the recursive checks for the symmetry. What we are doing, we are passing this 2 to 2 and recursively calling it, and it is checking. Is this number equals to this side or it is not? Okay. Now, what could be the base case of this in this condition? The base case for recursion is when both left and right subtrees are empty, indicating a symmetric structure, and we will return true. If only one of the subtree is empty while the other is not, okay, then we will return false, as this violates the condition of the symmetricity. Now we will understand the code. Okay, so there is this function boolean is same tree, and tree node p, tree node q, it is given. Now, for this condition where p double equals to null and q double equals to null, return true. That means I have told you if it is null, then you simply have to return true. Okay. Now, if in this condition, if p is not null and q is null, then the trees are not mirror images, okay, of each other. So the function will return a false in this case. Same as in this case, if it is not, it is null, and if it is not, then we will return false again. Okay, for this condition, where if q value double equals to the p value, and we will recursively call this function for what condition? When p is left and q is right. Okay, let's say p is left is this and q is right is this 3 value. For 3 we will check for 3, and then the same for p right and q left. Okay, if these condition satisfies, then we will return true. Okay, otherwise we will return false. And this is the condition where we are calling our function. Okay, so I guess it was very easy. And it is also working fine. Now we will move to our next question. That is flatten a binary tree to a linked list. Okay. Let's understand this question. Given a root of a binary tree, flatten the tree into a linked list. Okay. The linked list should be same tree node class where the right child pointer points to the next node in the list, and the left child pointer is always null. Okay. The linked list should be in the same order as the pre-ordered traversal of the binary tree. Okay. Now understand this. In the given binary tree has a pre-ordered traversal. Let's say 1, 2, 3, 1, 2, 5, 3, 4, null 6. Okay. So what we have to do here, now we have to flatten the tree. That means we convert it into a linked list. In this linked list, the nodes follows the same order as the pre-ordered reversal. Okay, is that clear? Now the right pointer of each node in the linked list, that means the right pointer of each node in the linked list serves the function of the next pointer. Okay, you will understand this via code. Additionally, we will set the left pointer of each node to null. This process is done in some place, meaning we modify the existing binary tree to the linked list. Okay. Next question is, this is null. Output would be null as well. The root is 0. Only one element. We will return that only element. Okay. So what could be the optimal approach or the best approach that we can think of is that Morris reversal is an algorithm. Okay. In this case, we will use a Morris reversal. I'm explaining it to you. What happens in this algorithm is that it allows pre-order and in-order tree reversal without using any extra space for stack or recursion. Okay, it utilizes threaded binary trees to traverse the tree without requiring a stack for saving the path. Okay, let's say this is the example 1, 2, 3, 4, 5, 6. Now, what this one will do, it will visit the node and move to its left child. Okay, then what does 2 do? Again, the same thing, visit the node and move to its left child. Now, this 3 will goes to 4. Like, no left, 3 has no left right children, so move to the right subtree of the parent. And what is the right subtree of the parent? That is 4. Okay, now there is no left or right child. Okay, so what we will do, we will move to the right subtree of the parent. What is the right subtree of the parent? That is 5. Okay, so there is no left child. We will again go to the right side. That is 1. So how is it working? Like 1, first we have 1, then we move to 2. Why? Because it is the left subtree of this 1. Then we move to 3. It is again the left child. Then we move to 4. Why? Because 3 has no left or right child. So we will move to the right side. That is 4. Now, we will check for the 4. Is there any left child or right child? No, there's no. So we will return the right children. Okay. Right subtree of the parent. That is 5. Now, we will check at standing at 5. Is there any left subchild? No, there's no. So we will move to the right child. That is 6. So we will return this linked list. Okay. I'm explaining you the code, what I have done. Now this is the function void flatten. Okay, this function takes the root of a binary tree and flattens it into the linked list in place. Okay, now this condition, it is very simple. This is the base case. If the root is null pointer, there's nothing to flatten, so the function returns immediately. Now a stack is used to perform depth first traversal of the tree. Okay, this is the stack for depth first traversal. Now the root is pushed, in this case, the root is pushed onto the stack to start the traversal. Now for this while condition, the loop runs as long as there are nodes in the stack. Okay, this loop is responsible for visiting each node in the tree. How? Let's understand. Let's say this is the tree node. The current node, this current is set to the top of the node. Okay, this one of the stack. Now the node is then removed from the stack using pop function. Now we will check for the condition. This is first condition. What it says, let's say if the current node has a right child. Okay, so it pushed onto the stack. If it is a right child, so it will push on to the stack, and this ensures that after processing the left subtree, the right subtree will be processed. Okay, you cannot jump directly to the right subtree. First, you have to check for the left one, and then only you can proceed with the right subtree. Okay, and now for this condition, what it will do, if the current node has a left child, it is pushed onto the stack. The left child is pushed after the right child to maintain the correct order, as the stack is LIFO, last in first out structure. Okay, now for this condition, if the stack is not empty, the right pointer to the current node is set to the point to the node at the top of the stack. This effectively links the current node to the next node in the pre-order traversal sequence. Okay, and this is the last step. What we will do, the left pointer of the current node. The left pointer of the current node is set to null pointer because in the flattened linked list there should be no left children. Okay, and this is the close. This is how it works. I'll run it. It is accepted. Now we will move to next question. That is mirror tree. Okay. It is again same as we have done symmetric tree, but no worries. We will understand this one as well. It is same, guys. Okay, so given a binary converted to its mirror. In this, what you have to do, okay, in this question, we have simply said true or false. We checked in this symmetric tree, we checked is it a symmetric or not. But in this mirror, we have to create a mirror tree for this. Okay, let's say this is the input 1, 2, 3. And what could be the output? That is 3, 1, and 2. You can see first we have choose the right element, and then we move to the head, and then we go to the left subtree. That is post order. Okay, so how is it creating? It is also again easy. Now let's understand this. So what you have to do, this function takes the root of the binary tree and transforms the tree into its mirror image. Okay, so simply you have to do, first you have to find the base case. Like what should be the base case? Base case is like if the root is null, that means the tree is empty, there's nothing to mirror, so the function returns immediately. This is the base case. Okay, now in this condition, now what could be the next step? Another base case is that if the current node is the leaf node, if the current node is the leaf node, in this case, what we have to do, that means both left and right children are null. Let's say for 4, both left and right children are null, and it is the leaf node. Okay, so it doesn't need to be mirrored, so the function returns. Okay, while this condition is not strictly necessary, as swiping null pointers has no effect. Okay, it's included here to avoid unnecessary recursive calls. Otherwise there will be a lot of recursive calls, like we are recurring it for 1, 3, 2, 5 again and again and again. For stopping that condition, we have to put this again alternative base condition for this question. Okay, now the left child of the current node, that is root left, is stored in a temporary variable, that is x. Same, this root right is stored in a temporary variable, that is y. And this is done to facilitate the swapping of the left and right children after the recursive call. Okay, like swiping, this is the right one and it is swiped to the left one. For this condition, we have taken these temporary variables in which we can store these right and left side of the tree. Now this function is called recursively. Now this function, that mirror function, is called recursively. Why? On the left child, first for the left child and second for the right child. Okay, these recursive calls ensures that the subtrees of the current nodes are also mirrored before swiping the left and right children. Okay, Now, this is the last step. What we have done in this, after the recursive calls, the left child of the current node is set to the y. That means the original right child. And the right child of the current node is set to x. That means the original left child. This effectively mirrors the current node by swiping its left and right children. Okay. Now this return, what does it mean? The function returns after completing the mirroring process for the current node and its subtree. Okay. It is working. Now we will move to another question, that is children sum in a binary tree. Okay. Just give me 1 second. Okay, let's understand this question. What does this means? Given a binary tree of n nodes. Okay, I have read this question. Now I'm explaining it to you. Let's say in a given binary tree, you have to convert the values of its node to follow the children sum property. Okay. Now I'll explain you in simpler words. Let's say this is a tree node. Okay. What does this question says? Children sum in a binary tree. So as you can understand, you have to sum the children's like 15 plus 5. What is the sum of these children? Is 20. Is 20 the parent of these two children's sum? It is. Okay. Then we will proceed to this one. 10 plus 5, that is 15. Again, it is true. Now 20 plus 15, that is 35. It is true. It is validating our condition. Okay. So we will return 1 in this case or true in this case. Why? Because we only have to check that if the children's sum is equals to its parent or not. Okay. In this case, in these leaf nodes which have no left trees or no right trees, so first we have checked for 15 and 5, that is 20, and then we have checked for 10 and 5, that is 15, and then we will check for 20 and 15, that is 35. Okay, so what could be the approach in this case? Let's say the constant constraint is that we cannot decrease the value of any node. Okay, let's say if there was 10 instead of 20, if there is 10, 10 plus 15, that is 25. Is 25 equivalent to 35? It is not, but 35 is greater than 25. So we cannot just decrease the value to 25. Okay, so that is the first base condition that you have to keep it in your mind. Okay, also the structure of the binary tree cannot be changed. You cannot change the structure of this binary tree. If we follow up bottom up approach, okay, in this case we will be following the bottom up approach. Okay, why? Because we have to check it from here and then we will move to the top one. So if we follow a bottom-up approach, then we will try to adjust parent value based on the children. Okay, we may reach to a situation where the sum of the children exceeds the parent's value, requiring us to decrease the parent's value, which is not allowed. Okay, with this, with just a bottom-up approach, we cannot guarantee that children's sum property will be satisfied at each level or not. Okay, so we have to check it. It might work for some cases, but not for all. There's no clear strategy to ensure that the property holds true for the entire tree or not. Okay, a key insight here is that there's no restrictions on how much we can increase the value of each node. Hence, we have the flexibility to adjust the values. Okay, we can adjust the values as our needs as needed to ensure the children's and property holds true at every node in the tree or not. So what algorithm we will be using, like how we will just solve this question, what could be it? So the base condition should be like by starting by checking if we have reached the end of the branch in the tree. If the current node is null, simply returning it. Okay, we are like end of the branch, then we just have to return null. Now then we have to calculate the children sum. Okay, so how we will calculate it? For each non-null node, calculate the sum of the values to its left and right children. This is the left one, this is the right one. You have to calculate the sum of these two children's. Okay, and if they exist, now what we have to do? We have to add up the values of these left and right children and store this sum in any variable. Okay, then what we have to do? Then we have to compare and update the value. Now comparing with what? Comparing with the parent. Okay, so let's say if we have stored the sum of these 5 and 15, that is 20, and then we will comparing it to its parent or its head node, that is 20. Is it equals to 20? It is fine. We will move to another condition. Okay, and if it is not, then we have to make some changes in the children itself. Okay, so let's understand this code. So what does it say? This function returns true if the subtree rooted at root satisfied the condition property or false zero otherwise. Okay. For this condition, if root is not equals to null, if okay. So what does it say? If root is null, the tree is empty. And by definition, it satisfies the children some property. So the function returns simply true or 1. If the root is the leaf node, that is, in this case, if the root is a leaf node, that means it has no left and right children. It also satisfies the children some property. So the function again returns a true. Now, in this case, in this int left and right, what is this? This line checks if the root has a left child. This one, checking for left child. Okay, it is checking for left child, and this would be for right child. Yes. So similarly, this line checks for the root for the right child. If it does, the value r is set to the data of the right child. Okay. If there is no right child, r is set to 0. Now at last we will return it. So the current node's data, that is root data, must be equal to the sum of the data to its left and right children. This condition. Okay. That means 20 should be equals to the sum of these 15 and 5. So this is what it is written here. And what we will do, we will and the left subtree also must satisfy the children sum property. Check with the recursive calling of this. We will recursively calling it. Now for the right subtree, we will again recursively calling it. Okay. If all these three conditions are satisfied and are true, the function returns true. Otherwise, it will return false. Okay. And this is the function where we have simply returns it. Okay. This is the next question, I guess. This is populating next right pointers in each node. So let's understand this. What does this question means? You are given a perfect binary tree where all leaves are on the same level. Okay. And every parent has two children. You are given a perfect binary tree where all leaves are on the same level. Fine. And every parent has two children. That is also fine. And every binary tree has the following definition. Okay. Populate each next pointer to point to its next right node. If there is no next right node, the next pointer should be set to null. Initially, all next pointers are set to null. Okay. Now, let's say in this input, given root is 1, 2, 3, 4, 5, 6, 7. Now the output is like 1 who it will point to. Can you see any right side, right subchild or right parent or right anything with 1? No, we cannot see. So we will simply return it to 1, to null. Okay. For 1, there's no right thing. So we will return to null. Now for 2, is there anything? Yes, there is. In this case, 3 is there. 3 is at its right node. So we will return 2 and 3. Uh, 2 and 3. And for 3, it is null. Why? Because there is nothing in its right side. So 3, after 3, we will return again a hash that is null. Then we will come to 4. Now we will check for 4. Is there any right side? Yes, there is. That is 5. So we will return 5. Now we will check for 5. Is there any right subtree or right parent or right child or right sibling or whatever? So yes, it is. There is. That is 6. So we will return 7 again. Now we will check for 7. That is null. Why? Because there's no right side of 7. So we will return simply hash, or that is null. For this empty tree, we will return empty node. Now we will understand this question, how we had done this. So what is the purpose? This function starts like the process of connecting the next pointers by calling the helper function connect right. Okay, this is the helper function, that is connect right, with the root of the tree and null as the argument. Okay. Now in this case, this one node connect right. So what is this? If root is null, the function returns simply null, which is the base case for the recursion. Okay, this is the base case. Now, this means that if there's no node to process or to proceed, the function does nothing. For this case, the next pointer of the current node, that means the next pointer of the current node, is set to point the node past is right. This effectively connects the right node to its right node. Okay, it's simple. Now for this, if and else condition, what does it mean? If the right node exists, let's say if the right node exists, the function recursively connects the next pointer. Okay, it will recursively connect this 4 to 5. Okay, why? Because 5 is existing and 5 is the right pointer for 4. Now passing the left child of the right node, that is right left, as the next right node. If the right node is null, the function recursively processes the right subtree, passing null as the next right node. Okay. Now for this connect right, we will again recursive function. The function then recursively connects the next pointer to the left subtree of the current node, that is root left, and the next pointer for left child of the root is set to the point to the right child of the root, that is root right. Okay, then we will return again simply root. That is after processing both left and right subtrees, the function returns the current node, that is root, and its return value is mainly useful for okay, and this is mainly useful for the recursive calls to maintain the structure of the trees as the function unwinds. So now moving to next question. That is search in a given search in a binary tree. So in this question, you are given the root of the binary search tree BST and an integer value. Okay. So find a node in the BST that the node's value equals well and returns a subtree rooted with that node. If such a node does not exist, return null. So let's say this is the example one, that is 4, 2, 1, 3, 7. Root is 4, 2, 7, 1, 3, and value is 2. So output is like 2, 1, 3. Okay. So in this given binary search tree, what we have to do? We have to search for a value that is 2. Okay. And then we will return that tree if it is existing with that value. Okay. In this case, you can see that 2 is at this position left of the root node. Okay. Is 2 creating any tree? Yes, it is. Because why? Because it has a right child, a left child, as well as a right child. So what we will return? We will return this tree, binary search tree, that is 2, 1, 3. Okay. Now in this question, 4, 2, 1, 3, again 7, and the value is 5. We will first search in this tree, is does 5 exist or not? So we can see 5 is not there, so we will return false here or null. Why? Because 5 is not present in this case. And it is pretty easy. Now let's understand this question. So first, our base condition is if the root is null, we will simply return it as null. In this case, function returns null, indicating that the value well is not present in the tree. Now in this condition, if root value double equals to value return root, let's say you have found the value that was 2 and you find in this tree, yes, it is present. So you will return that root. Else if the root value is greater than the value, then we will do a recursive call. Okay. For root left with that value. Else you will again do a recursive call for root right with its value. We will run this. Yes, it is working. Now we will move to our next question, that is convert sorted array to binary search tree. Okay. So what does this question says? Given an integer array nums where the elements are stored in ascending orders, convert it to a height balanced binary tree. And what is a height balanced binary tree? It is a binary tree in which the depth of the two subtrees of every node never differs by more than 1. Okay, fine. Now, in this question, the input is like -10, -3, 0, 5, 9, and output is like 0, -3, then 9, then null. Why? Because it doesn't have this side, and then -10, null, then 5. Explanation is what? Like 0, -5, 5, fine, that is, and 5 has nothing, so it would be null, -3, nothing, right side, null, and 9. So what we have done in this question, like we have converted this sorted array to a binary search tree. Okay, for this we have to like do recursive calls and recursion. Okay, for this case, what we will do in this purpose, this function takes a reference to the sorted arrays now. Two indices, we will take two indices, that is low and high, which defines the current subarray under consideration. Okay, it returns a pointer to the root of the BST constructed from its subarray. Let's say for the first condition, this if low is less than equals to high, that means if the base this is a base condition for the recursion. Okay, if low is lesser than or equals to high, it means that there are elements in the current subarray and we can continue building the BST. Now we will move to this condition, that is mid one, the middle index of the mid. of the current subarray is calculated. This middle element will become the root of the subtree for the current recursive call. Okay, that is what low plus high minus low divided by 2 is used instead of low plus 1, low plus high by 2 to prevent potential integer overflow. Okay, now this is a new tree node is created with the value of nums of mid, the middle element of the current subarray. This node will okay. So this root left side, this is the function concept to build the left subtree, and the left subtree will be built from the subarray to the left of the middle element, that is low to mid minus 1. Okay, the root of this left subtree is attached to the left pointer of the current node, and then we will simply return the root node. And at last, if low is greater than high, means the base condition, the current subarray is empty, so the function will return simply the null pointer, and this null pointer will be assigned to the left or right pointers of the parent node, indicating that there is no child node in that direction. Okay, so this is it. We will run it once. Is accepted. Now this is the next question, that is maximum product subarray. Okay.